Welcome to The Explainer. I'm absolutely thrilled you're here today. We are stepping right into the lab to break down a very specific, highly sensitive chemical procedure. We're looking at the exact preparation of a potassium hydroxide Pyrogallol solution. And you know, this isn't just about mixing powders. It's about precision, it's about safety, and really understanding chemical behavior at a fundamental level. Okay, let's dive into this. How do you safely prepare a solution that is so sensitive it must literally be hidden from sunlight? Well, that is the exact challenge we're tackling today. When potassium hydroxide and pyrogallol actually combine, the KOH creates this highly alkaline environment, right? And that environment supercharges the pyrogallol, turning it into a massively effective oxygen-absorbing solution. It is incredibly thirsty for oxygen, which actually causes a noticeable color change when it oxidizes. Because it's so sensitive to its environment, if we don't prepare and store it perfectly, the whole batch is going to be ruined before we even get the chance to use it. So here's the actual standard operating procedure document we're analyzing today. We're going to take this standard step-by-step recipe and turn it into a really actionable, engaging roadmap. By understanding the underlying why behind each of these bullet points, you'll see exactly how this reaction works and how to handle these materials like a total pro. Let's start with our first critical phase, materials and protective gear. Think of this kind of like prepping your kitchen before cooking a really complex meal, but, with much higher stakes. Careful preparation is the absolute foundation of lab safety and procedural success. So here's our complete inventory. We've got our active ingredients, pyrogallol, which carries the chemical formula C6H6O3, and our base, potassium hydroxide, also known as KOH. To bring them together, we'll need distilled water, a standard glass beaker, and a stirring rod. But hey, pay special attention to that very last bullet point. Protective gear, specifically gloves and goggles, is absolutely non-negotiable here. Potassium hydroxide is caustic, so we have to establish a strict foundation of safety before a single drop of water is poured.
Moving on to Phase 1, dissolving potassium hydroxide.
Now that we're properly suited up, this is where our procedure really kicks off. We're essentially creating the alkaline base environment that's going to allow our pyrogallol to react properly later on. Precision is everything in chemistry, right? We start by measuring out exactly 100 milliliters of distilled water into our glass beaker. And why distilled water? Well, any impurities or dissolved minerals found in standard tap water could totally interfere with the delicate, sensitive reaction we're trying to achieve today. So, the crucial point is getting our base concentration exactly right. To our 100 milliliters of distilled water, we're going to add exactly 10 grams of potassium hydroxide. This specific ratio is exactly what sets the stage for the chemical interaction to happen flawlessly in the next phase. Let's walk through the specific actions required here, because the way you mix this is just as important as what you mix. You take your 100 milliliters of water, and you slowly add the 10 grams of KOH while stirring. And look at that last step, ensure complete dissolution. You simply cannot rush this part. Every single bit of that potassium hydroxide must be fully dissolved into a clear liquid before you even think about touching the pyrogallol.
Which brings us to Phase 2, adding the pyrogallol.
This is basically the climax of our physical action. We're taking the active ingredient and finally introducing it to our newly prepared, perfectly dissolved alkaline base. For this crucial next step, focus your attention purely on the exact mass required, precisely 5 grams of pyrogallol. It's exactly half the mass of the potassium hydroxide we used, but honestly, it is the star of the show. When this compound hits that alkaline environment we just made, it activates, getting ready to aggressively trap literally any oxygen it touches.
Now, what's really interesting about this step is the emphasis on pacing. The operating procedure specifically instructs us to gradually mix the 5 grams of pyrogallol into the KOH solution and to stir continuously until fully dissolved. Because the resulting mixture is so incredibly eager to react with the oxygen in the air around it, we want a really smooth, highly controlled integration. Continuous stirring prevents clumping and guarantees a uniform, potent solution from top to bottom.
Let's move to and see how this builds into our final and perhaps most vital phase, safe storage and handling. So, you've just created a highly volatile, active solution. If you leave it sitting out on the open lab bench, all your precise measuring and continuous stirring will be ruined in a matter of minutes. Our entire goal right now is to prevent oxidation. The exact moment the potassium hydroxide and pyrogallol react and fully dissolve together, the solution starts hunting for oxygen. If it pulls too much oxygen from the open air, it oxidizes, degrades, and becomes completely useless for its intended lab applications. So our job is to basically freeze its potential until we actually need to use it. To successfully prevent that oxidation, The protocol details some very specific environmental controls. First, you absolutely must transfer the solution to a dark glass bottle. The dark glass blocks out light, which can actually degrade the chemical bonds. Second, you gotta store it in a cool, dry place away from direct sunlight. Heat and light are the absolute worst enemies of stability for this mixture. By sealing it tightly in dark glass and keeping it cool, we cut off its access to oxygen and light, perfectly preserving its reactive power.
This brings us to the end of our procedure, but hopefully it's just the beginning of your curiosity. We've seen how meticulously we have to guard this alkaline Pyrogallol mixture from light and air immediately after preparation, so I want to leave you with this question to ponder. What other solutions in your lab require dark glass to prevent oxidation? Think about the reagents sitting on your shelves right now. Understanding the why behind the storage turns a simple rule into an instinctive, brilliant safety habit. Thanks for joining me on The Explainer today, and keep questioning the science around you.